So we're doing the vertical and horizontal asymptotes in the first part of the worksheet. So, excuse me. So here are the rational ones. So you can compare what you have to this. And I shall slide it down. And now we'll worry about exponentials. So I'm just going to fill it in, I guess. And what happens? And -2, right? Based on transformations, right? Because you're moving down too.
How could you?
And Elon. So there's exponential and logarithmic. And now trig. Trig. So this might be more tricky. So why secant x? So where are we going to start with that? I don't know how much of this you guys did in 30-1. Could be a lot, could be a little. Secant. Did you do a lot with the secant, cosecant graphs, or just you saw them?
We saw them.
We saw them. I would recognize it on the screen, maybe. But.
I would recognize that it's one of the three. I wouldn't know which one.
Okay, so secant's 1 over cos, right?
Yes.
So then we want cos to be 0, and then secant will be undefined, and so for our domain, so when's cos 0? Like pi over 2 plus n pi. So we'll say x cannot equal pi over 2 plus n pi, right? Because that's where cosine is equal to 0. Yeah? So the does not equals is the domain, and the asymptotes, it becomes is equal to, right? It's where x is equal to. And a secant graph, what was these called? So it doesn't have a discontinuity, and it doesn't have a horizontal asymptote. Cosecant. So cosecant is 1 over sine, right? So we've got x over 2. What kind of a transformation is x over 2? The horizontal stretch, right? Because it's inside with the x by a factor of 2. Okay, so if we're horizontally stretched by a factor of 2, then that's going to change where our zeros are, right? So normally for sine, the zeros would be every pi, right? 0, pi, 2 pi, 3 pi. If we're stretched by a factor of 2, it's going to be every 2 pi. Okay, so the domain is it can't be a multiple of 2 pi, right? Because you put a multiple of 2 pi in here, when you divide by 2, it becomes a multiple of pi, which is where the sign is 0, right? Pi, 0, pi, 2 pi, 3 pi, negative pi, etc. pi. And so the asymptotes are where the domain is not, right? Sorry, not the, yeah, what? No, wait. Yeah, the vertical asymptotes. Because it's secant or cosecant, right? Tangent, 2x minus pi by 6. Whoa, okay, so let's rewrite this just putting it into a better form for transformation, right? So it's a tan of 2 times x minus pi over 12, because this way we get the shift, right? Because it's not shifted to the right pi over 6, it's shifted to the right pi over 12. right? Okay, so you got to factor that 2 out. So what's the tan? You know what the tan graph looks like?
Yeah.
Okay, so where is the asymptote? Pi by 2. So let's start. We'll do this in a few steps, right? So we'll just list for the tan graph, for just tan x. So let's say tan x. So x is not equal to pi over 2 plus n pi. Right? Because our first asymptote is pi over 2, and then the period of the tan graph is pi, right? Plus n pi. So the first transformation we're doing is what? No, you don't shift first. Oh, yeah, transformation. Stretch, yeah, transformation. Translation. Yeah. So it's a what? A horizontal by a half, right? Okay. So that means that. So let's do tan 2x. Tan 2x. So x is not. So we're going to take half of that, which would be pi over 4, plus half of this, which would be n pi over 2. Okay, because we're doing a horizontal stretch by a factor of 1/2, right? So the negative pi over 2 become negative pi over 4, and the period is now pi over 2. And now we're going to go right pi over 12, right? So that won't change the plus n2 pi, or n pi over 2, but it will change where this guy is. So where is this guy going to end up? Yeah, which is? So pi over 4 is 3 pi. Yeah, you're right. So that's 3/12, plus 1/12 is 4/12, but 4/12 is 1/3. So it's going to be pi over 3. It's okay. So this is this guy. Right? So we just got there a step at a time, right? Just applying transformations. So then, where are the asymptotes? Well, x is equal to pi over 3 plus n pi over 2. And there's none of those guys, right? Okay, so somewhere there's a statement of fact. Here it is. In this course, we will be using the concept of limits to determine vertical and horizontal asymptotes. Okay, so if we want to sketch a curve, we got to know where the vertical asymptotes are, right? We got to know where the horizontal asymptotes. That's all part of it, right? So right now, with curve sketch, we found maxes and mins, right? Local max, local min, absolute max, absolute min, based on the first derivative test, not a real test. And now what else? Well, we need to know where the asymptotes are, right? So first we need to know some general facts. If x equals a is a non-permissible value of y equals f of x, right? It makes the denominator 0 or whatever. And any of the following are true. So the limit as x approaches a from above of f of x is infinity, or the limit as x approaches a from above of f of x is negative infinity, or the limit as x approaches a from below of f of x is infinity, or if it's negative infinity, then x equals a is a vertical asymptote, right? Because what else do we have? If it's not a vertical asymptote, then it could be a point discontinuity. Okay, horizontal asymptotes. If the limit as x approaches negative infinity of f of x is equal to L, and the limit as x approaches positive infinity of f of x is equal to m, then y equals L and y equals m, right, horizontal lines, are horizontal asymptotes of y equals f of x if L and m are real. Okay. So in other words, as we go to infinity, what's happening? Are we approaching a value? For a few of the functions given in the table on the first page, use limits to algebraically determine the vertical and horizontal asymptotes of the following functions and sketch the behavior of the graph close to and on either side of the asymptote. Right. So that's kind of the key here. Is this analysis, this part of the sketch is just, we're just saying what's happening by the asymptotes, right? So what's going on there? If we want to know where there's local max and mins, we've got the other stuff to do that. All right, so starting with y equals 5x squared plus 10x over x squared. So we'll just start by factoring that, right? Okay, so what we're really worried about then is 5x over x minus 3, right? Because when x is -2, we know we have a point discontinuity, right? All right, so we are interested then in, so where is this undefined, right? When x is equal to 3, so we're interested in what's the behavior of this around 3. So we're going to do the limit as x approaches 3 from below, right? Because we know that, both branches could be going up, or one up, one down. We've got to figure out what the behavior is, right? And then we'll draw a little sketch just to show that. So the limit as x approaches 3 from below of 5x over x minus 3. So we can look at that and say, all right, so what's 5x going to be, right? Like around 15. Okay. Slightly less than 15. So let's just call that a relatively small positive number, because what's this going to be? Almost zero.
From the negative side.
From the negative side, right? So it'll be a really small negative number, okay? So we've got, 15-ish, so about 15, over a small negative number. So what's that going to give us? A really, really large negative number, which we will call negative infinity. Okay, so that's negative infinity. And how much space do we have? Well, let's just do this x squared. So the limit, so what if x approaches 3 from above? What's that going to give us? Well, so about 15 again, over really small positive number, right? So small positive. And the result will be positive infinity. Okay? And we want to do the horizontal asymptotes, right? So, horizontal asymptotes. So the limit as x approaches plus or minus infinity. So sometimes we could just leave it like that. We don't really have to look at positive infinity and negative infinity separately. Okay, so we'll start off by just writing that. The limit as x approaches that of 5x over x minus 3. Okay, now we have ways of doing this, right? So algebraically, we divide by the lowest power, or the highest power of x, I guess, right? So we take 5x over x, and we take x over x minus 3 over x, right? Which gives us 5 over 1 minus 3 over x. So what happens to 3 over x as x approaches infinity? It approaches, no, as x gets really big, 3 divided by a really big number is 0. So it becomes 0. So now the question comes, do we need to examine plus infinity and minus infinity differently, right? So we say, okay, so if this is 0, we're just going to get what? 5, right? So is this going to change the sign based on whether this is positive? No, it's not, right? I mean, it's 3 over x. So Yeah, if it's 3 over a positive, that would be a really small positive number. You'd have 1 minus a really small positive, but that's still basically positive 1. And if it's 3 over x and x is going to negative infinity, then it's a really small negative number. So now you're a little bit above 1, but it doesn't really matter, right? Because they're still both positive. So ultimately, it's just equal to 5. Okay, and so that's how we know as we go to infinity, are we going to approach 5 from above or from below? Right? Is by looking at this and saying, so will it make a difference where we're coming? Like, are we going to be 4.99999999999, you know, or 5.000000001? All right, now do we have room to sketch this? So we do have something going on at -2, right, which we know about, and then we've got +3. And we've got 5, right? So let's put the 5 in there. So that's what's going on there. And this is doing that there, and it's doing this here, right? And I guess if we want to kind of, I'm not really sure what's happening in here, okay? But we're not really interested in that, right? We're interested in what's happening as we go to infinity and negative infinity, and what's happening as we go approach the value of x equals 3. Okay, that we're going up there and down there. Okay, so again, we're just looking close to and on either side of the asymptotes, right? Okay, keep going. Y equals e to the 3x plus 1 minus 2. Okay, so we know for this that there are no vertical asymptotes, right? It's just, that's basically, it's just an exponential function, right? So it's just, you're playing an exponential function. No vertical asymptote. So vertical asymptote, none. Horizontal asymptote. Okay, let's start out the same. The limit as x approaches plus or minus infinity of e to the 3x plus 1 minus 2. So we might say, well, there's different things are going to be happening depending on whether we're going to positive infinity, right? Because you go e to positive infinity, that's just going to be really large, okay? So that there will be no horizontal asymptote as we go to positive infinity, right? So what we really need to just look at is the limit as x approaches negative infinity. Okay, and what's that going to be equal to? -2. Yeah. So you just think of it, that's e to a large negative number. Large negative. Okay, which would be 0 minus 2 or -2. Okay, and so to sketch -2. Actually, I guess we could sketch in the asymptote line. And just say that's what's going on there, right, in the vicinity. It's just coming down to -2. Okay, and it's coming down to, right? It'll always be above -2. Because this will always be some really small positive number. Okay, e to a large negative is just going to be a small positive number from which you subtract 2, so you're going to be slightly above -2. Right? The ln of x minus 6 over 2. Okay, so we think about what does a log function look like, right? Remember that. It has a vertical asymptote. Okay, where did we figure the vertical asymptote was?
0.
Well, normally it would be 0, but this is x minus 6, right? So it's been shifted, right? What are the transformations in words?
It will move to the right 6. Is it right?
Yes.
Yes, but that happened after.
The stretch.
So it's horizontally stretched by a factor of 2. Okay, so vertical asymptote. And a log function or a ln function, right? Because ln log, I mean, same, it's just the base, right? They don't have a horizontal asymptote, right? I mean, it's going to climb off to infinity. So all we're interested in here is the vertical asymptote. And we don't want to approach 6 from below, because it doesn't exist there, right? So we're only approaching 6 from above. I suppose the lawn didn't disappear, right? So that's going to give us what? X minus 6 is going to be a small positive number, right? Can't have negatives. If you have a small negative, well, you can't do that. So we're going to have the ln of a small positive divided by 2, which is going to give us what? No, you see what the log graph looks like. They kind of start down here. And then, so as with the log graph, as you are approaching, okay, just normal log graph, as you're approaching 0, what's it doing? It's going to negative infinity, right? Okay. Watch the base. I mean, if it's log base a half, then it's going the other way, but this isn't. Okay, so the ln of a small, that's negative infinity. Okay, so if you want to sketch that, call that 6, and that's what's happening there. Okay, remember, we're just interested in the vicinity. Okay, now, using limits, algebraically determine the vertical and horizontal asymptotes of the following functions and sketch the behavior of the graph close to and on either side of the asymptotes, right? Okay, again, very important that we do either side because we don't know. Is it going up to positive or infinity? It's vertical asymptote, right? And we know it's going to infinity, but is it positive or is it negative? So we have to examine either side of each asymptote. All right, so where are the vertical asymptotes? Yeah, so we need to be looking at x equals 1, right? So vertical asymptote, x equals 1. So we need to examine what happens as we approach 1 from below. So the limit as x approaches 1 from below of 3 minus 2 over x minus 1 squared. Okay, what's the squaring going to do? It's going to make it positive, right? So the denominator is always going to be a small positive number, right? Okay. So this will be 3 minus 2 over a small positive, which is equal to, yeah, so it's going to be negative infinity, right? Because we're subtracting, 2 divided by a small positive is positive infinity, and then we're going 3 minus positive infinity, so that's negative infinity. Okay. So negative infinity. What's going to happen as we approach 1 from above? The exact same thing, right? Because it's still going to give us 3 minus 2 over a small positive, which is negative infinity, right? Okay. Now, had that just been an x minus 1, then we would have had a positive infinity and a negative infinity, right? Sign would have changed. Okay, and horizontal asymptote. Limit as x approaches plus or minus infinity of 3 minus 2. 3 minus 2 over x minus 1 squared. Okay, so we're going to have infinity minus 1, and then square it. which is going to give us an extremely large number. Or we're going to have negative infinity minus 1 and square it. So we're going to get an extremely large, or sorry, positive number, right? So when you're taking 2 and dividing by that, you're just going to get 0, right? So it's just going to be 3. So that equals 3. And then we can go 2 over large positive. And we've got 3. Okay, so now we can sketch. So let's put this guy in. 3. So notice it's 3 minus, right? So we're going to be coming at the 3 from below in both instances, right? And what else we got? We got 1. Lost the 1. Okay, so we know that approaching from below, we are going down. And going this way, we are going this way. And we know that approaching 1 from above, it's going down. And that way it's going that way, right? And they're both approaching 3 from below, whether you're going to positive infinity or negative infinity, right? Because it's 3 minus, and there still is. It's really a small number, but it's a really small positive number, right? So 3 minus a really small positive number will be below 3 in both instances. Okay. Now we can see how that would change, obviously. If this guy were coming from above, then it would probably be approaching here from above, right? Coming down to 3. Okay, next. Oh, wow, okay. Sine x tan squared x for x is 0 to 2 pi. That's the next one? Yes. Okay. So, tan, where's tan undefined? Pi over 2. And in 0 to 2 pi, where else? 3 pi over 2, right? Okay. So we need pi over 2 and 3 pi over 2. I had a fisherman's friend. So what do we got to look at? We're going to look at 4 things, right? So pi over 2 from below, pi over 2 from above, 3 pi over 2 from below, 3 pi over 2 from above.
Isn't a fisherman's friend a worm?
Fisherman can have many friends.
It's not even a gummy. It's not even a sugar-free gummy. You know where that comes in. I don't think it's sugar-free. All right, so limit pi over 2 from below. I'm just do them one at a time, I guess, right? Write it all down. What is it? Sine x tan squared x. Let's move the below over here a bit. Sine x tan squared x. Tan squared x. What's going to happen there? But when you square the tangent, so we know the tangent can go to negative infinity, right? So tan squared x is always going to be positive infinity, right? Okay. So keeping that in mind, that kind of helps us a bit, right? So what's the sine of pi over 2 as you approach from below? Not that it matters, because, or does it matter? Let's see, where's sine? No, because sine is peaking, right? So it's 1. So we got 1, and the tangent's going to be positive infinity, right, squared. So we're going to positive infinity. What if we approach pi over 2 from above? Okay, so sine x approaching from above, still 1. Tan squared x, still infinity, so still positive infinity. And now 3 pi over 2. Okay, 3 pi over 2 from below. So what's
Sorry,
-1? And tan squared x, still going to be positive infinity, right? Because we're squaring it. So this will be negative infinity. And this will not be any different, will it? And infinity, -1. Okay, so sketching. Let's do that. 0, pi, so pi over 2, 3 pi over 2, there's pi, there's 2 pi. Let's get some asymptotes in there. Okay, so pi over 2 from below, where are we going? Infinity. Pi over 2 from above, where are we going?
No further.
Infinity, yeah, and no further. I don't want you going beyond infinity. Who was the Buzz Lightyear, right? Okay, and at 3 pi over 2? Now we know the sign of pi is 0, right? So we know at this point it's going to be on there too, right? But that's beyond what we're doing right now. So this thing's going to probably kind of come through here a bit, right? And then it's going to have to hit 0 here again. But, right, we're only interested in close to the asymptotes. Okay, and there's no horizontal asymptotes, right? Question?
At the end of this course, like when we're done with this, are we going to be expected to be able to extrapolate that information and draw out the full graph?
Well, yeah, we could do that now.
Well, yeah, so is that going to be a course expectation, or are we only
It'd be an expectation on this test, right? So,
Okay.
so part of the test is going to be, okay, so we've done the max and mins, right?
Yeah.
Okay, so you got all those. Now we're doing the, okay, what's happening at the asymptotes?
Okay.
So you're going to know, wait, there's an asymptote here. All right, I don't know what's going on. I have to do this analysis around the asymptote.
Yep.
So I think there's going to be a question basically where you're going to run through the whole gamut, right? So
Okay.
here's the equation. What are the vertical asymptotes? What are the horizontal asymptotes? Okay, what's the max and the min, right? You do the first derivative and blah, 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 right? And then draw a really accurate sketch.
Yeah, sure.
Okay, and the last page. And then tomorrow's work period, right? A special case. What happens when you mix an exponential with a polynomial? I believe that's not legal in certain southern states, so.
Haha, that's funny.
But hey, the new host of the Daily Show is South Africa. Well, the incoming Trevor Noah.
Oh, that guy. Isn't
John Stewart's retiring.
Why?
He's old and tired. I don't know.
He got old.
Well, he's got a career directing films now or something. Okay. 2 to the x over x squared. As we go to positive infinity. So what's 2 to the x going to be?
Biggest time, you know.
Really, really big. What's x squared going to be? Okay, now is it even bigger or is it not quite anywhere near as big or is it just as big?
It doesn't matter.
Alright, so what's 2 to the 10th?
Large number.
Yeah.
1024. What's 10 squared? 100. This one you can do. Alright, so if we go to 15, 15 squared is 225, but 2 to the 15 is a little bit bigger than 1024. Right, like 2,000, it's like 32,000. So how's the top growing?
Slowly.
No, the top. 2 to the x. That's going.
I stick by my answer.
We have really, really large.
And really large.
Really, really large. Over kind of large. Kind of, sorta.
Or just really so.
Biggish.
fat person in America versus a fat person anywhere else.
So if you're taking an extraordinarily hugely large number and dividing it by something that's going to not that big.
Fat to the board.
Sorry, am I offending all the Americans here in Canada?
I think what it says is that the top is going to grow just that much faster that the bottom really won't even have much of a say when you start getting out into really large numbers. Because a million squared isn't that big. That's 10 to the 12. Right? Big deal. But, or wait, multiplying points right now. It's 10 to the 12. But 2 to the million, that's big, man. All right. So if we go to negative infinity, what's 2 to the x going to be? Yeah, like really 0, kind of, eh? Zero-ish. And what's x squared going to be?
Still kind of sort of big-ish, but larger, right?
Well, it's going to be huge, right?
It's still the same.
Well, it's kind of sort of big-ish. Okay, so kind of, sort of, big-ish. In a positive way. Okay, wait, and that's also in a positive way. Oh no. It's okay. So what's 0 divided by kind of sort of big-ish in a positive way? 0. Likely 0. Okay. The limit. Oh, God. X squared over 2 to the x. So we're going to get a kind of a sort of biggish number over a really, really large number, right? So what's kind of sort of biggish over really, really large?
0.
Yeah, probably. Kind of sort of big, but in a positive way. Over unimaginably large. Unimaginably.
Unfathomably.
Unfathomably. How many fathoms? Unfathomably misspelled large. So probably 0, right?
Fathom's 8 length change, right?
Yeah. There's rods and there's chains, and fathoms is pretty much nautical, right? There's no. I once had to wheel, like Judge Doggedly, you had to measure the length of the course, and then these measuring wheels. We had one that measured in rods, I think, or something, right? Like it's this huge old thing. Okay, as we go to negative infinity, then x squared is going to be kind of sort of large, but in a positive way, right? And 2 to the x is going to be 0-ish. And so that's going to be infinitish. Now it says 2 of these will require more investigation, apparently. So we will use your graphing calculator, but we'll use my graphing calculator, because I brought it. I know, right? It's like, okay, so y1, we're going to graph that as 2 to the power of x. And y2, we're going to graph as x to the power of 2. And y3, we're going to graph as y1, vars, y vars, enter, divided by y2, vars, y vars, enter, down, enter. And we're going to turn off y1 and y2, because we don't want to see them. So all we're going to look at is the black graph. So as x approaches negative infinity of 2x over x squared, we can see that we are coming down to nothing. And as we approach positive infinity, we can see that that's really growing and it's going to positive infinity, right? Sure. So what we said was what? And you can go into the table and look. So there's an error. So these guys are getting smaller, right? As we go to negative infinity, it's getting kind of small. And as we climb, so, you know, it's getting big. Now it's really starting to pick up some steam here, right? It's 102.56 and so on. Okay, so turn off y1. So now let's graph y2 divided by y1. Go off there. So let's get rid of that, and then divided by and
That should be the answer to every test. That should always be correct if there's the answer.
that's kind of an interesting graph, actually, right? But so negative infinity is going to infinity, but positive infinity. It's interesting. It kind of comes up here. So that's, you know, on a test you could find that maximum, right? Local maximum. Absolutely not. So as x goes to positive infinity, this goes to 0. So in general, exponential functions, where b is greater than 1, grow to infinity blanker than polynomial functions. Faster, stronger, higher. Or is that Sidious, Altius, Fortius? I think it's the Olympic motto.
Oh, I thought you were doing the Kanye West song.
Oh, well, he stole it from the Olympic motto.
Tomorrow.
Use limits. Using limits. Algebraically determine the vertical and horizontal asymptotes of y equals e to the x, an exponential function, over x squared minus 4, a non-exponential function, what do you call it, quadratic, I guess, and sketch the behavior of the graph close to and on either side of the asymptotes, right? So remember, all of this asymptote stuff just gets us the close to and on either side of the asymptote. What's going on here? We get all the rest of the information from the stuff that we've been doing, right? All right, so where are the asymptotes? So plus or minus 2, right? So now we got to do 4 things. Right, we got to do minus 2 from below, minus 2 from above, plus 2 from below, plus 2 from above. So limit as x approaches negative 2 from below of e to the x. All right, so we're going to end up with e to the negative 2. Which is 1 over e squared, which is, yeah, what, quarter or 9. It's just some kind of smallish positive number. But what do we get on the bottom? So smallish. Smallish positive. And x squared minus 4. So now it really matters, right? Is this positive or negative?
Oh, wait. Yeah. No. Negative. Negative.
Negative, right?
Yeah.
Okay. So, it's a negative number. It's a really small negative number. Really small negative. So a small positive divided by a really small negative is? Negative infinity. All right, so negative 2 from above. So you're thinking negative 2 from below, you're thinking like negative 2.1, right? I mean, that's kind of e to the x over x squared minus 4. So the e to the x isn't going to change, right? It's still just going to be e to the negative 2, or close. So smallish positive. And negative 2 from above, the 1.99999 squared minus 4. It's going to be a small negative. Yielding negative infinity.
subtract 2 from below, it should be a very
Small
small
positive number.
So I was right. Oh.
You're right. Really small positive number, right? Because it's going to be bigger than 4. Right, when it's squared, it'll be larger than 4. Whereas below 2 squared is going to be smaller than 4.
How does it feel to be wrong?
Would there be a horizontal asymptote when x equals
You
2?
wish.
You wish you
You
were.
were the
You
opposite.
can't have a horizontal asymptote when x equals 2. You can have a horizontal asymptote when x is infinity.
You're to my left. That's science. Yeah.
I guess.
There's a vertical asymptote.
Yeah.
Yeah, we're going to do those next. We're halfway through the vertical asymptotes. We've fixed our mistake. So the limit as x approaches 2 from below. Okay, so we get e squared. You know, big deal, 9, whatever, less than 9. And we get x squared. We're approaching 2 from below, 1.99. Squared minus 4 is going to be small negative, right? So small negative. Okay, small positive. Let's just say e squared. So negative infinity. And as we approach 2 from above, e to the x over x squared minus 4. So e squared over small positive, right? Because now we're coming from above 2, so we're going to have a number that's just above 4. Minus 4, this will be a small positive. Which leads us to positive infinity. Okay, now we need to look at horizontal. Okay, horizontal asymptote. Limit as x approaches plus or minus infinity of e to the x. Okay, do we need to examine these separately? I think we do, right? Because e to the infinity is going to be a little different from e to the negative infinity, right? Okay, so we can't just look at these together, right? Because there's different behavior going on. So we're going to need to split this. So limit as x approaches positive infinity. All right, so now we come down to that. Okay, we've got an exponential up top. We've got a quadratic on the bottom. And what's that limit then as we go to infinity? Infinity, right? Because the exponential grows faster than the quadratic. And the limit as x approaches negative infinity. So e to the x is going to approach 0, right? And x squared minus 4 is going to be 4 less than infinity squared. Not your box? Zero. Okay, so now we can sketch out the behavior, right? What's happening around the asymptotes and what's happening with the horizontal asymptotes. Where we can sketch this out. Let's go down here. Okay, so we have asymptote at negative 2, positive 2, and what are we doing here? So, all right, negative 2, what's happening? Negative 2 from below is positive infinity. And as we go to negative infinity, well, really shouldn't sketch the whole thing in there. So that behavior is there. And this behavior is going out here. And this guy is coming down here. and negative, or sorry, positive 2 from below is here. Okay, so something's going on in here. We don't know what, right? Like peaking somewhere likely, and that. And here it's coming from there, and then it's going off to infinity, right? So no horizontal asymptote here, just behavior. And we use our other stuff to fill in the blanks, right? Fill in what was their local maximum between negative 2 and 2, right? So we derivatives and all that good stuff. Okay, done.